Okay, here we are, the last week, week 4, Calc 1, day 16, chapter 5, section 1. Unbelievable. So I would strongly suggest this week, as you go through these videos, that you also go back and review the videos beforehand so that you can be prepared for our last exam. Today we're going to look at areas under the curves. This is what we use a lot of integration for. For instance, if we have here y equals f of x and we have y equals g of x, we want to know what the area is that are bounded by these two functions between a and b. That's what we're going to take a look at today. Now, the same idea as we used before when it was area under a curve and bound by the x-axis are the rectangles that we have here. And you can see we can do the similar thing here with the rectangles by approximation. So this approximation appears to become better and better, of course, as you get more and more rectangles, just like before. The smaller and the more rectangles you have, the more accurate you can be. So that would take us to a limit as n approaches infinity from 1 to n, number of rectangles of the first function minus the second function, and that will give to you the area between the two. So the area of A in the region bounded by the curves and the lines A and B, if f and g are continuous and f of x is bigger or higher than g of x for all x in this interval from and including A to and including B, then this will be your general statement that you can make here symbolizing the area. So let's go forward and do some examples. Okay, we are taking a look at page 345. We are looking at example 1, keeping in mind, well, let me use a pen because it's darker, keeping in mind that looking at figure 3 on 345, and I'll go there quickly here. Figure 3, we are going to take this area under f of x and this area under g of x, and we are subtracting them to get the area that's left just on the inside, okay? So once again, figure 3 shows the area under f of x minus the area under g of x. And that will be what we're looking for, the total area in between those two. Okay, so example 1. Example 1, we have y equals x squared plus 1 bounded by y equals x. We are going to look at it from x equals 0 to x equals 1. And so what we're looking at here, the area under the curve would be from lower bound 0 to 1 upper bound. We're going to take this value, x squared minus or plus 1 minus this value, x, and we are integrating that whole thing dx. And I can just simplify that a little bit before I do. Make it look a little nicer. So we have x squared minus x plus 1 dx. Okay, so now when I integrate this using my, what I call the opposite power rule, we have x cubed over 3 plus x squared over 2 plus x. And now we have it bounded between the upper and lower bounds 0 to 1, so we do not put a plus c. We're going to put those values there, and we're going to plug 1 in first. So when I plug my 1 in, I will have 1/3 minus 1/2 plus 1. And then I'm going to plug in 0, which will give me 0. So 0, 0, 0. And when I simplify these fractions and combine them, I will get 5/6. Okay, as simple as that. All right, let's go to example 2. Are they all simple as that? No, of course not. Okay, so example 2, we have enclosed by y equals x squared and y equals 2x minus x squared. Okay, so figure 6 takes a look at this on how they intersect. You should look at the graph before each one. As a matter of fact, above that figure would be figure 3, where we looked at our y equals x and our x squared plus 1. That's what we were looking at in the last problem. So in example 2, we have y equals 2x minus x squared tells me that I'm going to have this parabola that is upside down here and flipped, right? Because I have a negative in front of the x squared. And then y equals x squared, which is my parent function parabola right here. So we're looking at this intersection on the inside, okay? So let's take a closer look at it. Now calculating that, I see that the one that is upside down is going to be coming through first. So I'm going to have, and again, did it say where we were looking at this? It says find the area that is enclosed. So what you have to do is figure out the system of equations where these will have their endpoints. So when we figure out the points of intersection for our system of equations, that's where we will set these two equal to each other and solve. And I'll do that real quick. So I have x squared equals 2x minus x squared. Just as a review, move this over. Okay, I'm going to go ahead and take this over and set it equal to 0. Factor out a 2x. And I see my x values are 0 and 1. So I will go back and plug that in to one of my functions so that I can get my y values, and I will find my points 0, 0, and 1, 0. Okay, that's how I know what my upper and lower bounds are. So I'm going to have from 0 to 1. Okay, my x values. And knowing that my graph, and again, I'll just kind of try to sketch. You know how my art is not so great. So try to sketch here. So I'm coming up. We're talking about 0 to 1. Okay, this is what we're looking for. So I see that this one is on top. So that's important because I need to put it first. So I have 2x minus x squared. Okay, and then I'm going to subtract from that my parent function parabola, which is x squared. So that is my integral set up. Okay. Now here we go. Now I'm going to, of course, simplify it a little bit. So now I have 2x minus 2x squared. And again, these two are assembled together, dx and the integral. And now I'm going to integrate. So I have 2x squared over 2 minus 2x cubed over 3. And that is going to be measured between 0 and 1. my upper bound and lower bound. And we're going to reduce, of course, this is just x squared minus, I have 2/3 x cubed. Again, and it's all, I always like to put parentheses here so it's clear that it's both of those. All right. So when I plug 1 in, I will have 1 minus 2/3. Okay, when I plug 0 in, I will have 0, 0, so it's just minus 0. So 1 minus 2/3 is going to be 1/3. And that is my answer, 1/3. Okay? Alrighty, that takes us to example 3. Example 3 is an interesting looking graph. And you might say, well, how do I graph these? How do I know what the graphs look like? Well, if you're not real great at graphing by looking at it visually, then you use the graphing calculator simply. And we are going to take a look at x over the square root of x squared plus 1 and y equals x to the 4th minus x. So we have this graph right here. And then we have this kind of interesting looking, almost like a parabola looking function underneath. So the question was, approximate the area bounded by the curve. So once again, we have to figure out what our solutions are. However, this one is really difficult to do that. So we actually will have to use a graphing calculator and hit our trace button to go through. Now this I can see is 0, 0. So that makes me happy. So I'm going to have a lower bound of 0. But over here, I'm not real sure. Let me get a pencil. I'm not real sure about what this would be. So I'm going to have to go through my graphing calculator, and as I travel up to here and I get close to this area, possibly zooming in and finding out what value this is going to be close to. Now I want to get an approximation as close as possible so that I can get a good result for my area. So let's take a look at what the book says we'll find about 1.18. So 1.18 is the number that we're going to use. Let's look at the area between 0 and 1.18. Now, by inspecting my graph, I see that this function, my x over the square root of x squared plus 1, is on top, and then my y to the 4th function is underneath. So I'm going to take this minus this. So I have x over the square root of x squared plus 1 minus x to the 4th minus x dx, of course. All right, so now I'm going to integrate the terms, and I need to take a look at these separately because I can see here by using the substitution rule I'm going to have my du, u du right here. So let's take a look at that. We can handle it. We did it before. So my u value will be x squared plus 1. So therefore my du value is 2x. So I say, what do I do to 2x to get what is there, which is just a 1x, right? And I would multiply this by 1/2. So this will end up being my adjuster for my first part. So I have area equals 1/2 on the outside, and I'm still going to take a look at this, but this time I'm going to write it with my u. So u to the negative 1/2. Here is my u, here's my du, okay? All right, now my upper and lower bounds. Here is where a problem like this, it's probably going to be easier to redefine them based on what my u value is. So in order to figure that out, I'm going to take my u values and I'm going to adjust my bounds. U equals, now I have my lower bound was 0, so that would be 0 plus 1. So now my lower bound is 1. Okay, now my upper bound is going to be 1.18 squared plus 1. And I'm going to put that in a calculator and round it to the hundreds place, since that's where my number was rounded to start with. Usually a good rule of thumb, look at what's given and stick with that. So I have 2.39. So those are my new boundaries for when I'm going to integrate. So now my second part of this is still going to be from 0 to 1 because I haven't changed this to u du over here, dx. So I can split this up and use two different methods. Real important, right? Let's go ahead and integrate. So my first part is 1/2. This will be u to the negative 1/2 plus 1, 1/2 over 1/2. Okay? And now after I do that, when I can see when I invert and multiply, the 2's will reduce, so it leaves me with u to the 1/2. Let's see what I have over here. Well, don't forget my bounds on this side are different. They're 1 and 2.39. So I come over here and I have x to the 5th over 5 minus x squared over 2. And this negative on the outside will be distributed through, and I have my bounds of 0 and 1. So when I distribute that through, I will have negative x to the 5th over 5 plus x squared over 2 from 1 to 0. And that's what this looks like. Okay, now I just need to evaluate what my values would be. So I have the square root of 2.39 minus the square root of 1, which is just simply 1, minus 1.18 over 5 plus 1.18, oh, this is to the 5th power, squared over 2. Okay, let's see. Do I have anything else here? If I plug in my 0, I get 0. So that's all I get here. And then, of course, my square root of 1 is just 1. So when I simplify this, actually you put it in your calculator. You can put parentheses in here and just put it straight through your calculator and you will get approximately 0.785. It's a nice number. Okay. Okay. And that again was example 3. Alrighty. So, example 3 is finished now. What about example 4? Now we're going to take a look at something a little bit different. Let's see if I want to start on a new page. I might want to. Example 4. I think we're all right. All right, so let's take a look at the chart that's given to you. Here in this chart, we have two cars, and it shows the velocity of the two cars. And they're side by side. So the area between the curves represents the distance between the velocities of the two. So we know that the area under the velocity of curve A is by car A during the first 16 seconds. So from 0 to 16 seconds. Similarly, B from 0 to 16 seconds, in that time period. So the area in between the curves, which is the difference of the areas under the curves, is the distance between the cars after 16 seconds. So after they're driving, this is how far they are apart. Okay? Looking at that, here is my A curve, here is my B curve. This represents my A, this represents my B curve. And this represents my difference between velocity of A and velocity of B. Now, in order to do this, I might want to use the midpoint rule to help me break down some intervals. To use all of these numbers, not necessary. So I might take a look at, let's say my values are from, let's say the width is going to be 4 with our n value of 4. So how do I figure that out? Well, let's go back and review. Get my pen back here. I don't want to put this too far away. Let's do it like this. I think you can see both. All right. Okay, so we're going to take a look at the width of the rectangle, and remembering with my midpoint rule, I would take B minus A divided by my N. I have said that I'm going to use N being 4. So that's 4 intervals. So when I do that, this is 16 minus 0 over 4. So my width of my intervals is 4. Now, when I take a look at my chart, this is where I'm going to get my numbers. So I'm going every interval of 4 to do this. So the midpoints from 0 to 4 would be 2. The midpoints from 4 to 8 would be 6. The midpoints from 8 to 12 would be 10. So that means I'm looking at the midpoint from here to here. That's 13. The midpoint from here to here, 23. From here to here, 28. And from here to here, 29. Okay, this is where I'm getting my numbers. So now I can set up my integral. So my integral is from 0 to 16. And I have my, what is on the bottom of the chart, my velocity of A minus my velocity of B, and that is with respect to time. So that would be my delta T. My delta T times the sum of those differences. The differences are already taken care of here. So I have my delta T times 13 plus 23 plus 28 plus 29. You can see most of the work again was done for us in the chart. Now my delta T we found to be 4. So my delta T is 4. And when I add these together, I will get 93. So I will get 372 feet. 372 feet. Okay? All right, now let's talk a little bit about sometimes the area between curves could change. Like one could be on the top and then on the bottom and then switch, and then that means you would get a negative value. So if you look at figure 9 here, taking a look at figure 9, you see my red curve, which is my f of x here, and this one is my g of x. Now the problem with this is if I take f of x minus g of x, I'll get a positive value. But if I take f of x minus g of x here, I'll get a negative value. And then if I take f of x minus g of x here, I get a positive value. So if I'm looking for the total area and I add these, I'm not going to get an accurate answer because I'm going to be subtracting this in the middle. So I have to really examine the curves to know what I'm looking at. And in this case, I'm going to want to take the absolute value of this one in the middle, add these two together, and then add the absolute value. So here is the definition, similar to the definition of absolute value of x. We're going to say f minus g when f of x is bigger, because it's going to be positive. But when g of x is bigger, then you're going to take g of x minus f of x. This is very similar to the actual definition of the absolute value of x. Okay, so that is what we're doing. So let's take a look at example 5. Example 5 has something similar going on here. We have our cosine and we have our sine. If I take my cosine minus my sine, I'll get a positive area here. Excuse me. But if I take my sine minus my cosine minus my sine here, I'll get a negative value. So I'm going to have to do something about that. So we need to know, where does this happen? Well, from our basic trig class, we should be able to remember that at pi over 4 is where these two will intersect. So I need to take my my integral and split it. From 0 to pi over 4, I'll have cosine minus sine. And from pi over 4 to pi over 2, I will then have sine minus cosine based on that definition. So let's take a look at doing that. Okay, so here I have my beginning statement. When I look at the graph, and I'll try to put the graph in here again so you can see it right here. Okay, there we go. Okay, so when I'm first looking at it, I'm saying, okay, I'm talking about the area from 0 to pi over 2 of the absolute value of cosine x minus sine x. So wherever it's negative, I want positive. And that, of course, is dx. So I'm going to take the area of the first one plus the area of the second one. Okay? So when I examine this again, I see from 0 to pi over 4, I'm okay. I don't have to reverse it. So I have from 0 to pi over 4 cosine x minus sine x dx. However, from pi over 4 to pi over 2, I will get a negative value if I don't reverse them. So I need to reverse it to be sine x minus cosine x. Now by doing that, I will have positive areas on both sides, so I can just solve it straight through and not worry about losing any of the area that I'm looking at. So let's go ahead and integrate. So the derivative of cosine is sine x, and the derivative of negative sine x would be negative cosine x, where the derivative of sine x is negative cosine x. So we have a negative and negative, and that's positive. So this is from 0 to pi over 4. Plus, on the other side, again, if I integrate sine x, I'm going to get negative cosine x minus the derivative of, or the integral of cosine x would be sine x. And this is from pi over 4 to pi over 2. When I start substituting these values in, I will have 1 over the square root of 2 plus 1 over the square root of 2. Then my sine of 0 is 0, and my cosine of 0 is 1. So here I'm going to have 2 over the square root of 2 minus 1. Now moving on to the other side, when I'm substituting my values in, I have my pi over 2 values first. So I will have a negative, well, it's a negative 0, so it's just 0 minus 1. And then my pi over 4 values again are 1 over the square root of 2 and 1 over the square root of 2. So as I am simplifying that, I have negative 1 plus 2 over the square root of 2. So now I just need to combine that together, and then of course I want to rationalize it. So when I rationalize it, I will get 2 square root of 2 minus 2 as my final answer. And that is example 5. Example 5 on page 347. Hard to believe. Okay. All right. So now let's take a look at a different instance. What if we have curves that are bounded by the curves and not necessarily bounded by my x values, but what about my y values that it's bounded by? So we're going to take a look at a couple graphs, and then we're going to do a problem like that. Here's an example of two curves. You have g of y and you have f of y here. And it is bounded by c and d on the y-axis versus the x-axis. So when we have something like that happening, now we're going to be taking our rectangles are going to be horizontal. However, it doesn't do anything with the area. The area of the rectangle is still the area of a rectangle no matter how whether it's vertical or horizontal. So we have to remember that. And we also need to remember for this instance here, if I have this area and I'm looking at bounded by the y, so I'm looking at the area that is, I would say, smaller than this x value here, or this function, and then I'm going to subtract from that the one on the left. So they call it the one on the right and the one on the left, which makes sense. So one on the right, one on the left, and you're going to subtract the two. Okay, so we're going to take a look at example 6. Example 6 has a similar look. Here we have 1/2 y squared minus 3 as our parabola that is sideways, and then I also have my y plus 1 linear equation. So when I do that, again, I'm going to take my right minus my left because I'm looking at this area that is bounded by the 2. First thing I need to know is where do these intersect? So I do have to do my system of equations here. When I do the system of equations, I will find that my intersection points are -1 to -2 and 5 to 4. So keep in mind that this time I'm looking at my y values and not my x values. So when I set up my integral, my area is going to be -2 to 4. And I'm going to take my value on the right minus my value on the left. So my value on the right is y plus 1, and my value on the left is my 1/2 y squared minus 3. So again, here is, if I solve this for x, because that's how I'm looking at this using the y-axis, I would solve this for x and get y plus 1. And I would solve this for x and get 1/2 y squared minus 3. So I want to take my right value minus my left value. So I have y plus 1 minus my 1/2 y squared minus 3. Okay? And of course, we need to simplify that a bit. It doesn't really make sense the way it is right there. So let's take a look at negative 1/2 y squared. Looks like plus y and plus 4. And this is, of course, now dy. And I'm looking at from -2 to 4. Okay? So from here, you do everything else the same. So I'm going to take negative 1/2 y cubed over 3 plus y squared over 2 plus 4y. And of course, simplify that a little bit. Negative y cubed over 6 plus y squared over 2 plus 4y. And that will be from -2 to 4. So now when I plug in my values, I will get negative 1/6 times 64 plus 16 divided by 2 is 8 plus 16 minus 4/3 when I put -2 in to get -8, and then that'll be a positive and reduce, plus 2, square the -2, I'll get 4 divided by 2, and finally minus 8, 4 times -2. Okay, so now when I take that all together, I will get the result of 18. And that's it. So it's really not too bad. You just have to make sure that you're capable of looking at your graphs so that you can get a good idea of what you're dealing with. Now, that is the last example for section 5.1. Today we will do one more section, 5.2, and then starting on Tuesday we will do one section of a day so that we have a full day Thursday for reviewing for our final test. Thank you, and I'll see you at the next one. Peace.